Good morning. So today I want to talk about Landauer formula. So let's consider a thin wire, something like that, and this thin wire is connected to two large reservoirs, and so this length is L and this length is W. I'll call this one left reservoir and this one is right reservoir. So this is our thin wire. So a couple of assumptions about this wire. So we first assume this has like a uniform width with W much less than L and no disorder or no impurities. So electrons in principle should propagate without any scattering. And we also allow no inelastic process, no phonons, no electron-electron interaction, and we need L much bigger than W so that we have quasi 1D wire. Also, for this calculation to work, we need K Fermi, which is the characteristic momenta of the waves, times W is not large. It's not too large. Good. In this case, we can we can find eigenfunctions and eigenenergies of this wire. Let me write that. Psi nk of x comma y is equal to. So first there is like this particle in a box solutions, n pi over wx in this transverse direction, and there's also like plane waves in the horizontal direction, and this is 1 over L e to the I kx, and corresponding energies E and K are h bar squared k squared over 2m plus h bar squared pi squared 2m w squared times n squared, where n is equal to 1 to ... m is band mass. So for brevity, I'm going to call this factor gamma, and so this n we are going to call it subband index. So the picture is something like that. So we have one band which is quadratic. Let's say this is n is equal to 1, and there's like the second band, third band, and so on. So this is n is equal to 2, this is n is equal to 3. So this is E of k, so this is k. So one more assumption is like we are going to assume no reflection from reservoirs back to the wire. So we are assuming like a reflectionless wire, and the size of right and left reservoirs L is much bigger than dephasing length, so that when the electrons enter into one of the reservoirs, they just equilibrate. And the question we want to ask is, what is the resistance of the wire? Okay, let's try to calculate that. We assume let's assume chemical potential on the left is bigger than chemical potential on the right, and here's our one band, something like that, and we have one chemical potential on one side, another on the other side, mu left, this one is mu right, and since all the electrons that are moving to the right like this, they should come from left, and all the electrons that move to the left, they should come from right. Then this chemical potential is going to determine the occupied levels. These are the occupied levels that are moving to left, and these are the occupied levels that are moving to the right. Now let me try to write the current. The current is equal to, suppose we have two spin indices, so this is spin, and we need the sum over all subband indices from 1 to infinity, and we need to integrate over all possible k's, minus infinity to plus infinity, and this is the phase space volume. Need to put minus charge, and so here I need to put here in total I need to put current density, which is minus E over delta T, and minus E over delta T is length of the wire divided by velocity, right? Then this is going to be minus E over L, V, and K. So this is minus E over L, this is V and K, and this is now we need the occupation probability of like a mod here K, which is given by Fermi function. This is F of epsilon and K measured with respect to mu left, and this mod should be moving to the right. I'll put like a theta function for that, plus F of epsilon and K minus mu right. Let me push that. And this one should be moving to the left, minus K. Now this V is group velocity, which is 1 over h bar d epsilon and K dk, and from this relation we can see that the group velocity does not depend on index n. The derivative is only taken with respect to here. And what I can do is I can also like convert this integral. So this, okay, let me write first. So this is going to be minus 2e. So I can cancel this L with the L. So cancel this 2 pi with the h bar. So this is 2e over. So this is dk, and I'm going to write this is d epsilon k dk. So this one does not depend on n, and I have f of epsilon k plus gamma n squared minus mu left, and this one goes from 0 to infinity. And we can do exactly the same thing for this term, and then change the integral from integral variable from minus k to plus k, which will give us minus f of epsilon of k plus gamma n squared minus mu right, and close the bracket like this. But this term, I can change the integral variable, like cancelling these two. So this is going to be like this is d epsilon of k, and in the 0 temperature limit, f of epsilon, the Fermi function, is going to go to theta function minus epsilon, I think. Then this is going to be theta function. This is also going to be theta function, which is going to be mu left minus, let me write it like epsilon tilde, and epsilon tilde, I can absorb this gamma in the integration variable and take the integral from gamma n squared to infinity. And similarly here, this is mu right minus some left. And lastly, when I look at this and the theta functions, this is just energy integral. So we have like a system like this. There's like one chemical potential here, one chemical potential there. All these states are occupied. So what this integral is going to give is is the energy difference between these two chemical potentials. Let's write that. This is going to be minus 2e over h. N is equal to 1 to infinity. Actually, let me write it in a different way. So this is going to be mu left minus mu right times n, and here n is going to be number of states in this little interval. N is equal to 1 to infinity. This is theta of mu minus gamma n squared, and here I'm assuming mu left is approximately equal to mu right is approximately equal to some mu, and if you want, you can also consider this to be like number of occupied channels, which can be like 1, 2, 3, 4, 5, which is an integer. So this is number of so-called open channels, which is an integer. Good. Now, for the chemical potential, we are going to use mu left minus mu right. There will be like an applied bias here, and the applied bias is going to be like external voltage difference, and that external voltage difference is going to determine the difference between chemical potential as like that. And if you put that here, so we find I is equal to 2e squared over h. This is h times n times v. Therefore, conductance G is just the coefficient here, is going to be 2e squared over h times n. here this 2e squared over h is equal to 1 over 25,812.807 ohm. Actually, I think this is not without 2. So this is this denominator is what we call resistance quantum, and this one is conductance quantum. Here's the experimental verification of this result. Here, the conductance of a thin wire is measured as a function of gate voltage, and you can see there are like these integer steps. This is n is equal to 1, is equal to 2, and is equal to 3, showing like Landauer quantization. Good. So what we have is like a wire without any impurity has a resistance and this resistance is determined by number of channels, or if you want, because the occupied number of channels is going to be determined by W, it's determined by W. We call this thing like contact resistance, or sometimes injection resistance, because the electrons that are like higher energy here, they just go through wire and enter the lower energy and they equilibrate. In that process, in the equilibration process, they like dissipate energy by, I don't know, creating phonons and other things. As a result, we are saying that this is like a resistance due to contact. And because it doesn't depend on like local impurities in the wire, we say that it is like global or sometimes non-local conductance, because it doesn't depend on local quantities like impurity, but it depends on like global things like geometry of the wire. Now we can also consider the case with single impurity. Let's just consider the same problem but with just one impurity. So I just put like an impurity here, so this is impurity. And the formula can be generalized easily to this case. What we need to have is like, we have like some incident wave, and this wave is going to be transmitted with probability t, and it's going to be reflected with probability r, and it's going to be transmitted with probability t. Then in the Landauer formula, I think I can take it from here. This. All we need to do is, this is current. Here we need to put, so this is T square. For states that are moving to the right, we need to have this transmission, and for states that are moving to the left, we need to have this minus 1 minus r squared. But we know 1 minus r squared is t squared. So this formula is going to lead to something like that. This is 2e squared over h times t times v. And t here is going to be n is equal to 1 to infinity. Each channel is going to have its like reflection and transmission probabilities. We are going to square that and sum over all channels. And then this formula gives us G as 2e squared over h t, which is known as Landauer formula. Now I want to consider the case of this single impurity in a little bit more detail, maybe like in more than one impurity, and demonstrate something called universal conductance fluctuations. So the setup is something like that. I have like one impurity separated by some distance and a second impurity. Suppose the distance between them is like L12, and I have an incident wave, and which is going to be reflected with A, and this can be transmitted B, and when it reaches to here, this same wave is going to have like an additional phase. Let's call it like B times e to the I phi, and phi, because these are like waves moving with Fermi velocity, it's going to be from, this is k Fermi times L12. We are using e to the I kx form of waves. And here it is going to be reflected as c times e to the minus I phi. And this phase is going to be coming here, and this is c. And there will be another transmission here, and we are going to call it d. And in this problem, we need to determine transmission probability, which is t given by square of d, needs to be determined to find the conductance of this setup. So let's write, we can write down the Schrödinger equation, solve it in terms of e to ikx and e to the minus ikx, but at the end we are going to like match these coefficients. And let me write the conditions here. So the first one is on this interface, we need to have B, which is transmitted, should either come from, like let's call this T1 and R1 for transmission and reflection from left hand side, and this one is going to be T2, R2, transmission and reflection from left hand side for the second impurity. And if it is transmission and reflection from the right hand side, I'm going to put primes. So this is T1 times 1, right? This 1 is transmitted with probability T plus, or this C is reflected from right. This is R1 prime times C. So primes are reflection and transmission from right hand side. So this is the first equation. the second equation, we can write exactly the same thing for this interface. So d is going to be equal to, and there's only one thing which can be can be transmitted with amplitude 2 t2 times b e to the I phi. And lastly, this c can only be coming from the reflect, because there is no incident from here. This c can only be coming from the reflection of b, and we are going to write this like c times e to the minus I phi is equal to R2, this is reflection from left hand side, b times e to the I phi. Solve. So I want to solve b is equal to T1 plus R prime 1 times C, and D is equal to T2 times exponential, D is equal to T times B times exponential I phi, and we have C times exponential minus I phi is equal to R2 times B times exponential I phi, and I want to solve this for B, C, and D. Okay, I think so. This is B is equal to T1 plus R prime 1 C. D is equal to T2 times, I think I need to put B here, so here B, and this is C times the exponential minus I phi is equal to R2 times B. I think this is correct, and this D seems to be correct. Okay, all I need is this D. Let me write that. So D is equal to, okay, I'm going to absorb this minus here, so this is T1 T2 e to the I phi divided by 1 minus R1 prime R2 R1 prime R2 e to the I 2 theta, the 2 phi. Okay, I think that's it. And now I need to calculate T, which is absolute value of D squared, which is okay, the absolute value of T1 is going to be T1, absolute value of little t2 is going to be T2, so T1 is equal to T1 squared, T2 is equal to T2 squared divided by, and so I need to calculate the denominator. Let me do it on the side. So this is 1 minus R1 prime R2 e to the I 2 phi times the same thing, complex conjugated. So this is times R1 prime complex conjugate, R2 prime conjugate, and this is, and this one is going to be 1 minus, so this thing I'm going to write it like R1 prime R2 e to the I 2 phi minus R1 prime star R2 star e to the minus I 2 2 phi, and the cross terms are going to be R1 times R2. But this term I'm going to write, so here I'm going to write it as R1, R2 cosine of some phase, and this total phase is the phase of this entire complex number. So let me write this. So this is going to be, actually let me write it like with 2. So this is 1 minus 1 plus R1, R2 minus 2 R1, R2 cosine theta. Good, and this is the desired result. First, even in this form, it is telling us a couple of things. So because using Landauer formula, G is equal to 2e squared over h times t, for this formula, the conductance G depends on not only single impurity quantities like T1 and T2, but also on L12, the distance between the impurities through theta. And in some sense, this geometry is kind of like a Fabry-Perot interferometry. So there's like some incident wave coming, and there's like some reflected wave going like this. And these two waves, like right moving and left moving wave, can be interfering constructively or destructively on this interface. And by moving one of the impurities just a little bit, you can have like maximum interference or minimal interference. As a result, this T for changes like changes in L12 by like a little bit, like which is 1 over k Fermi, which is like a very tiny number, is going to give a result where T is order of 1. You can change transmission and reflection from 0 to 1 by just changing the location of second impurity. And that means change in conductance delta G is going to be equal to 2e squared over h, which is a universal number. Let me finish with one last comment using exactly the same problem. Let us consider resistance, or rather like impedance of the same wire. So it is going to be like Z is equal to, it's going to be proportional to 1 over T, and there will be an overall factor which I'm going to put later. And to extract the contact resistance, like I only want to see the resistance due to these two impurities, and I don't want to see the contact resistances. And it is reasonable to subtract 1 from this. And total resistance is going to be H over 2e squared. Then I have this T, and I need to like, okay, let's take this T. Yeah, so if this is T, so this is 1 over 1 over T minus 1. So this is what I'm trying to calculate here. And this one is equal to 1 plus R1, R2 minus 2 R1, R2 cosine theta minus T1, T2, entire thing divided by T1, T2. And this T1, T2, I'm going to write it like 1 minus R1, 1 minus R2, which is going to be equal to 1 minus R1 minus R2 plus R1, R2. And this one is going to cancel this because of this minus sign. And this R12 is going to cancel this R12. And this result is going to give us Z. So this is the equivalent resistor. You can think of this as like one resistor here and another resistor here, and we are kind of like calculating the equivalent resistance of two resistors connected in series. So this Req is going to be equal to R1 plus R2 minus 2 R1 R2 divided by times cosine theta divided by T1 T2 times H over 2 E squared. So if we had only one impurity, Z1 would have been H over 2 E squared R1 over T1, and if we had only the other one, Z2 would have been H over 2E squared R2 over T2. But what we see from this formula is ZEQ is not equal to Z1 plus Z2. Earlier in the discussion of Aharonov-Bohm effect, we have seen that resistors connected in series, they don't have G is equal to G1 plus G2 because of interference effect. And similarly, resistors connected in series are not going to have R1, R2, Req is not equal to R1 plus R2. This is due to quantum interference. So let me use this formula and finish it with one last discussion for what is coming. So we can consider impurity averaging. So this is like it's kind of like some averaging, but I'm going to call it impurity averaging. And let's look at ZEQ average. And the only thing I need to average here is the cosine theta average, right? Because there's nothing else to average here. And the average of cosine theta, 0, because cosine theta changes from -1 to +1. So then this average is going to be R1 plus R2 divided by T1, T2, H over 2E squared. And if we consider it, if we compare it with, again, Z1, H over 2E squared, R1 over T1, and Z2 is equal to H over 2E squared, R2 over T2, what we see is this quantity is bigger than Z1 plus Z2. So on average, resistance is bigger than independent resistors. So this is again due to interference. And what this tells us is that there's like an enhanced backscattering, which suppress transmission. And this is actually a precursor to what we call Anderson localization. Okay, I'm going to stop here. Next time we are going to start talking about Anderson localization, and it'll probably take a couple of lectures for us to understand what that is.